I'm Nathaniel Roth. I go by Nathan. I'm a finishing PhD student at UC Berkeley. My advisor is Dan Kaysen, and I'm talking about work that I've...
Can you put on the microphone?
Oh, the microphone. Yes, sorry. Sorry. And so I'm talking about work that I've done with my advisor, Dan Kaysen, and also James Guillachon and Enrico Ramirez Ruiz. And we're all here because Svi and company organized a wonderful conference for us, but the reason they did that is because TDEs are very mysterious. There are a number of puzzles that we're all trying to track down right now, and these are three that we've kept in mind throughout the course of our work. The first is what we just heard about, so I won't say much more than that, other than just to reiterate the point that we do see TDEs now over a wide range of wavelengths at optical and X-ray, sometimes simultaneously. And so the big picture that I think we're after here is figuring out, can we predict how often a disruption emits at each of these wavelengths, and then can we use that information to refine our predictions about the rates that we'll see the events at different wavelengths, and then resolve some of the tensions that we currently have between the predicted rates and the observed rates. Something else is the notable lack of color evolution in the optically observed TDEs. So here are just two notable examples of that, PS110JH and PS111AF. So as the optical flux dropped, the shape of the optical continuum isn't varying very much. And what this suggests to us is that we have to maybe think beyond simple black body models of the emission, unless for this to happen in a black body sphere, you'd have to have some sort of ubiquitous conspiracy between the luminosity and the radius of the photosphere. And then, of course, there is the question of the optical lines, the great H alpha debate. This is the plot that Yair showed us yesterday with the diversity of spectra, some with broad helium-2 and no signs of hydrogen, all the way down to some that do show both the helium and the hydrogen. And a lot of work to understand this so far has been done with photoionization calculations using tools like Cloudy that are really tailored for situations where the optical depth of the environment is low, but as we'll show later here, a lot of the lines we think are forming in regions that are optically thick to electron scattering, and that will have a profound effect on both the lines and the continuum that you see. So what this suggests to us is that now is a good time for radiative transfer studies to explore some of these questions in detail, and as I said, move beyond simple black body pictures for the flux and understand the emission lines in a more optically thick environment. So to run a radiative transfer calculation, we need to choose some geometry. We have to simplify the problem initially. These are expensive calculations. And so to start, we've taken a spherical geometry. And I want to say a few words now about why that is relevant to the problem, although it doesn't, of course, there's room to improve on our geometry in future investigations. But simulations of disruptions show that in addition to an elliptical accretion disk that forms, you can also have a sheath of material at larger radius that might be intercepting some of the hotter accretion disk light and then re-radiating it at longer wavelengths, UV and optical. And this is reminiscent of a very old idea from Loeb and Ulmer, who predicted before any of the optical TDEs were ever seen that we might see optical emission from TDEs if you have material at large radii. In their case, they were imagining a radiation pressure supported envelope that was more or less static. There are some issues with a picture like this. You need to very finely tune the luminosity to right near the Eddington limit in order to support something like this. Other work has shown that when you exceed the Eddington limit, you might be able to allow the radiation to escape through channels in the polar regions and have something more along the lines of the zebra model that Coughlin and Beagleman have developed. You can also imagine that maybe the radiation does launch an outflow. Linda Struba and Elliot Quadrant did some work on this back in 2009. It's been revisited by Metzger and Stone. And here you do have an outflow, but you also still have this reprocessing idea where hot radiation at the center is intercepted by material farther out. So our current work has been more, it's more directly applicable to the static envelope, although we would like to look at these outflows in future work. And of course, there is now the idea for optical emission coming from circularization at larger radii. And this is also, I think, something we need to follow up with the radiative transfer. There is some connection to this idea and the way we have set up the problem, which I'll explain right now. So we are taking a spherical domain. We have an inner boundary and an outer boundary that we can adjust. We use a density power law that we chose to be r to the minus 2, although that could also be adjusted in future work. And we put in some thermal spectrum at the inner boundary, which is usually peaking in the X-ray or the extreme UV. And we choose the temperature of that inner emission to correspond to what you would find from the radiative diffusion equation. So for the optical depth of the envelope and for whatever luminosity is coming out at the center, you can find the energy density at the inner edge of the envelope. And you can translate that to a temperature. And then by adjusting the position of this inner radius, for example, by moving it out to several times the tidal radius, you can crudely incorporate the idea that you're getting dissipation not all from very close into the black hole, but also farther out. So the radiative transfer that we're doing is with Monte Carlo, and we alternate between solving the transfer equation and then solving the non-LTE rate equations, which give us ionization states and atomic level populations. And we track all of the bound-bound, bound-free, and free-free transitions. Well, I should say we track about 1,000 of the bound-bound transitions and a few hundred levels for the bound-free. We also have free-free processes, some collisional processes, although they tend to be subdominant to the radiative processes for controlling the ionization states of the material. Some simplifications to keep in mind. The composition of the envelope that we're looking at initially is hydrogen, helium, and oxygen, not other metals so far, just because it takes additional work to do the atomic modeling to include the other metals. Not that we don't think that they won't be, they could be important for some of the details of the lines that we see, but I think a lot of the general results still hold even with just the limited composition that we're looking at. We are using solar composition, so the hydrogen in all of the calculations I'm going to show you is about 10 times as numerous compared to the helium by number density. I already explained the power law gas density, the inner boundary. Okay, a big simplification to keep in mind is the way we've treated the line widths so far. So we've just, for the absorption and emission everywhere in our envelope, we're using a Gaussian line profile with a width of 10,000 kilometers per second, which was inspired by observations like PS110JH. And that is something that we also plan to explore in more detail in future work. I'll skip over the details about the way we're doing the non-LTE physics. Aficionados can ask me about this later, but I'll just jump now to the results. So here are some spectral energy distributions that we get coming out of our calculations. So on the horizontal axis is wavelength, covering all the way from 10 angstroms to 10 to the 4 angstroms. Lambda L lambda in ergs per second is on the vertical axis. And the two dashed curves that I've shown here are two different inner X-ray spectra that we put in that correspond to different locations of that inner radius. The colored curves are the reprocessed light that comes out. So you deplete some of the soft X-rays, and you get a fraction of them coming out at longer wavelengths like the UV and the optical. And if you integrate the optical luminosity here, you get a few times 10 to the 43 ergs per second, which is about what many of the optical observations show us. In these particular cases that I've showed you, you also get a lot of the X-ray coming out. And the reason that's happening is because even though the electron scattering depth is very high, the absorption optical depth is not necessarily very high at all wavelengths. Some of the ionizing photons can just scatter all the way out without ever being absorbed because the material is so highly ionized. Now, this doesn't always need to happen that you get all the X-rays out like this. We've experimented with dropping the luminosity, and here I should mention that this is dropping the luminosity, keeping everything else fixed. So this is not necessarily meant to show you a time series for a given event. This is just trying to build intuition for what happens when you change just the luminosity. Yes?
A quick question. What is the Aldrin inner radius in terms of gravitational limit for a black hole mass?
So the mass of the black hole does not enter directly into this calculation. We just chose a luminosity here of 10 to the 45 ergs per second. So you could, if you want to say a 10 to the 7 solar mass black hole will have, this will be the inner radius is for us tends to, in some cases, up to 100 times the gravitational radius.
Can you say again what is the calculation you're doing exactly? You have a mixture of three elements you mentioned. You assume it's a spherical situation and you release that luminosity in the center of it?
That's right. And so we're looking at a steady state solution. So we're not following the time evolution. We can just vary the parameters and then see what the final converged solution looks like as it changes. The diffusion time for us is about a week or two. So we're sort of imagining near peak and not following it for a time much longer than a few times 10 to the 6 seconds. What does the radiation that you emit at the inner boundary, what does it look like when it escapes? And that's...
So it's a steady state calculation for a given luminosity spherical.
That's right.
And you deposit the energy at about 10 to 13 centimeters? Is relative to
Yeah, the blue curve is 5 times 10 to the 13. We tried even smaller also, and it looks similar. You just imagine shifting the peak of the soft X-ray to smaller wavelengths, and it doesn't have a big effect on what comes out in the optical. Let's see. So that is, yes, I think that is helium, okay, 1800. Okay, 1800, sorry.
No, I'm just guessing the V on the scale.
So there's something going on at like the Lyman at 1200.
There's a chart, that looks sort of, it's a little hard to gauge with the log scale.
Yeah.
But I don't know, 1500 angstrom, carbon 4, or
Well, so again, we don't have carbon, so that might be an oxygen line. I should go in and identify which line that is.
It looks like a big feature, and there's one if that is robust against other parameter changes. Looks like.
So I've been focusing mainly on the lines that we see in the optical, but I think we definitely want to do more predictions for the UV.
We saw UV observation.
Yeah. So I haven't had a chance to really compare in detail to the UV observations just yet.
And the dominant cross-section in this situation is scattering or line or...
So scattering is the dominant opacity throughout, and then what's absorbed, electron scattering. Yeah, and so the primary process that is absorbing the soft X-rays is photoionization of helium-2. And in the optical, the primary absorption processes are either hydrogen photoionization or free at wavelengths greater than the Balmer break, so at 3,500 angstroms and longer. Here's what happens when we adjust the mass of the envelope, keeping the luminosity fixed, and the optical flux moves down while the shape of the continuum remains relatively constant, which is reminiscent of some of the data that I showed you earlier for events like 10JH. There are many steps to go before we say, well, this is exactly what is describing the evolution of the light curve. This is, again, just varying the mass, keeping everything else fixed. The point, though, is that this is just another aspect of the problem to keep in mind about how optical flux relates to parameters of the problem and how you can adjust the flux without adjusting the shape of the continuum. So how much time do I have left?
6
Okay. Okay. So let's take some time now to look at the spectra. So here are 3 spectra for envelopes where the parameter we varied was the outer radius of the envelope. And we've rescaled the units here so that all of their continua overlap right at 6,000 angstroms. And that was done simply to make the trend in the H alpha equivalent width more apparent. But what you can see is there is a transition where the H alpha sticks up noticeably above the continuum and then moves down and blends into the continuum. In fact, it moves into a slight absorption feature. And that's what we showed here when we subtracted off the lines and a power law continuum, which is the fit to what we have at these wavelengths. And what we see is a range of line ratios. So for the blue, it's about 2 to 1 helium to hydrogen. For the green, we have 5 to 1, which is that constraint that it's right where PS110JH is constrained to be. And then for the red, when you look at the actual spectrum, it moves into a shallow absorption feature here. But if you look back at the actual spectrum, especially with there's noise around the data at long wavelengths, it would be hard to distinguish from just pure continuum. So to understand how this is happening, we need to think a bit about effective optical depths in a scattering-dominated atmosphere. So for a given process, if you want to know how deep into the atmosphere you're seeing the emission from that process, you need to consider something called the thermalization depth, which is approximately 1 over the square root of something called epsilon, where epsilon is a ratio of whatever is the absorption opacity to the total opacity. And you can derive this effective optical depth from a random walk argument. It's an old result that goes back many years and underlies a lot of work on stellar atmospheres. And then to predict the flux that comes out at a given wavelength, you need to consider the thermalization depth at that wavelength and then integrate the emissivity in the volume extending from around the thermalization depth to the outer edge of the system. And so this is a plot where we try to show how this works at a glance. I've been thinking about ways to make this more clear, but I'll try to walk you through it here. So the y-axis is integrated emissivity. So we take J lambda ergs per second per angstrom per solid angle, multiply it by 4 pi. That's the that gets rid of the solid angle, and then integrate 4 pi j lambda times 4 pi r squared dr. So you're integrating that emissivity over a volume up to the indicated electron scattering optical depth on the horizontal axis. And then you stop at a given wavelength, the flux that comes out, you stop at around that thermalization depth for that wavelength. And so if we look at the red and the orange first, so orange is a continuum near H alpha, 6,000 angstroms. And the thermalization depth there is relatively far in, close to 30 electron scattering optical depths. And we want to compare that to what's coming out for the line plus continuum at the H alpha wavelength. So then for that case, you would add the contribution of the red and the orange curve together at the marked thermalization depth with the red dot. So you add those two together and you get something pretty comparable. So the H alpha is not going to stick up far above the nearby continuum. If you do the same exercise for the helium, the continuum for the helium is coming also from around 30 electron scattering optical depths. The helium line is less opaque to itself, so its thermalization depth is deeper into the envelope compared to what was happening for the hydrogen. And so when you add together the continuum and the helium at the 4,700 angstrom line wavelength, you get something that will stick up notably above the continuum. So I'll put up my conclusions here. I think the main takeaways are that this is a good time for more radiative transfer studies to connect all of the detailed hydrodynamic work that's being done to the observations. For the optical observations, we've shown that there's likely to be a lot of emission that's coming out at UV wavelengths and soft X-ray wavelengths that you might not be accounting for if you try to estimate the bolometric luminosity from fitting a single black body to the optical observations. And TDEs with simultaneous optical and X-ray coming out might be arising from these situations where you have partial absorption of the X-rays. And the line transfer is highly sensitive to optically thick effects. There's lots of room for improvement. I've mentioned a lot of those along the way, but I'm happy to now to hear your suggestions about future work. Thank you.
Thank you.
So you mentioned the metals not taken into consideration. So obviously this will take away some flux from the UV and
Yes.
the blue part. Do you have a sense of where, how far into the optical and how much of an effect it would be, or is that hard to
It's a little hard to estimate. I will say that when we started with just hydrogen and helium and no oxygen, and then later we added in the oxygen. And by adding in the oxygen, we saw a lot of new line features, especially near the 100 especially near 100 angstroms that weren't there initially. But the optical continuum and its behavior didn't change very much. The H alpha and helium line ratios didn't change very much. So my guess is that for comparisons to UV spectra, like the assassin event that we've been talking about, and for future observations, we'll need to include all those extra metals. But for some of these early questions that I tried to motivate at the beginning of the talk, I don't think it's super sensitive to that.
it won't hurt the constant color luminosity line?
Our experience so far is that I don't think so. I mean, maybe at small quantitative levels, but the qualitative trend I don't think will change. Yes?
In an earlier slide, you showed H alpha sort of coming in and out of existence
Mhm.
as a function of our outer.
Yes.
And do you have a physical explanation of what's going on, why that's important?
I've been thinking very hard about that. I haven't really arrived at a good intuition for that yet. It's a little complicated because what's setting both the emissivity and the thermalization depth are the exact level population distributions, which are given by this non-LTE rate equation matrix. And then we also need to be tracking that as a function of radius. And when we change the outer radius of the envelope, we're changing the densities in both the regions where the opticals, where the continuum's coming from and where the lines are coming from. And so I haven't really found a clear intuition for how all of that, at the end of the day, gives you that nice systematic trend without a radius. But it's something I want to keep thinking about. Yeah, well here, you can even see it here. There is something that's happening with the H alpha line as you vary the mass. So if you look at the purple curve, there's two spikes happening in the optical down there. That's the helium and the H alpha. And the H alpha is not really being seen for the higher mass cases. So this is another parameter where the H alpha comes in and out.
It might be fun to see how you think you can go away and sometimes does.
Yeah, definitely. The strength of the helium line is changing as well. We focused on the ratio to the hydrogen, but its equivalent width is changing as well. And it would be great if we could get a featureless continuum. We haven't gotten that yet, but that would be interesting to find.
I guess this is a question for the observers. So your spectrum is much flatter than a black body. Does that actually fit into the black body slopes that are maybe probably gained in here as more like lambda 1 or something?
I showed yesterday in the discussion actually these models of split data, and I think our observations still can distinguish exactly.
Yeah, I've been thinking about that too. So 10JH is a case where it really seems like you're seeing the Rayleigh Jeans tail. There are other observations where people have been saying, well, maybe you're getting close to the turnover off the Rayleigh Jeans tail, and you can fit a black body there. But you could also fit a power law there with a slightly shallower slope than Rayleigh Jeans. But I agree that I think this is a lingering question for us. Is there a way that we can get the optical continuum slope to be steeper? So far we've had trouble doing that. Maybe if we consider more of a shell geometry rather than having the emission extending over such a wide range of temperatures. That might be one way to do it. Yeah.
Yes, I think if you measure alpha, so the spectral index slope instead of the black body, you get around 1 sometimes. So I don't think you should change your model to get on a rate G scale. But my question was, so you have a steady state model, but based on the sources of opacity that you identify that are dominant, and can you say something about the diffusion time scale for converting X-rays to, say, optical?
Yeah. So the dominant the dominant opacity for setting a diffusion time is the electron scattering opacity. And we can do estimates of that, what the diffusion time should be, and we can compare it to our numerical results. And most of the optical depth is at smaller radii. Because we have this power law, most of the scattering is happening at smaller radii. So you don't have diffusion time is optical depth times radius over the speed of light. The question is, what radius might you need to use there? And it's actually, we see it's more appropriate to be using the inner radius for the density configurations that we saw. And so you get, both from that estimate and from the Monte Carlo, a diffusion time of about 10 to the 6 seconds for, say, this red curve here. So that's a week, something like that.
What is it? You're seeing the density, tau density?
Yes, we are taking r to the minus 2 is what we settled on. So, so that is the same density profile that you would get for a steady state outflow. There are ways that you could get a power law like that for a more static envelope. So these zebra models, for example, have density power laws that range from r to the minus 1.5 to r to the minus 3. We have tried exploring steeper power laws. The calculation does become more expensive the steeper the power law, because then the density at the inside gets higher, and we have to spend more time watching the photons diffuse in the inner region then.
How
But
about the flatten? How about the flatten?
This is the flattest that we've tried so far, but yeah, we should explore that parameter too. Brad's been waiting in the back.
No, sure.
I mean, I want to understand what you said these are steady state calculations. Even if you haven't said yet, you were involved in time,
What we're imagining right now is sort of a sequence of things like this. So at any given moment, one of our calculations can tell you what the, sorry. Go. So at any given moment on the light curve, you can take parameters from our calculation and try to match that to what's seen. And the time scale for the SED we're generating to adjust is short-ish compared to the time that the total light curve is evolving. So we're hoping that these snapshots can tell us about what's happening in moments in time. But the real way to do it would be a time-dependent calculation, where not only are the properties of the envelope changing in time, but you're also needing to involve that with the diffusion time of the envelope. And that might have something like that.
Okay, thank you very much.